Greetings of the day. Welcome to the course on Operations Research Technique. In this particular course, we have covered unit number 1, unit number 2, unit number 3 and unit number 4, which was project management. In unit number 4, till date, we have learned the aspects of PERT, Program Evaluation and Review Technique, and CPM, that is Critical Path Method. In that case, in PERT and CPM, we have studied how to interpret the given data and how to calculate various time estimates and find the probability of completion of particular project within the given time. PERT is basically related with, as we have studied in difference between PERT and CPM, PERT being probabilistic in nature. It is expected in problems or numericals pertaining to PERT that we are supposed to find probability of completion of the given project within the time frame. Whereas in CPM, that is critical path method, which is deterministic in nature, what we did is we have calculated different types of floats, namely total float, free float, independent float and interfering float. In both PERT and CPM, we have studied importance of slack and float. And now we are on the last part of this particular project management, that is cost analysis. And any project, as we have studied, consumes time as well as resources. When it consumes time as well as resources, then there is expenditure in the amount of resources and some quantity we are expending, and for that we have to pay some money. So what we have to do in this particular case is we have to find the balance between the time and cost in such a way that project is completed within optimum time and corresponding cost. So we'll see how the problem goes ahead. Now, as discussed, we have covered this PERT part, we have also covered CPM part, and now today we are on the very important topic of project cost estimation, that is, it is referred in operations research language as time, cost and trade-off analysis. We know any project consists of activities, and activities consume time as well as resources. So whenever it is time consumption, and we have seen that PERT is concerned with 3 time estimates: optimistic, pessimistic and most likely, whereas CPM activities, they are deterministic in one in nature and only one category of activity time in CPM network. Now, as you can read here, so this is the sentence frame given to you for understanding while discussing the scheduling of project activities in previous section. So we have seen in PERT and CPM that we schedule the activities in the precedence order, that is A greater than B, B greater than C, like that, and based on that we draw the network. The cost of resource, important is the cost of resources consumed by activities were not taken into consideration. So as I have said in earlier case, that is PERT and CPM, we have not considered this aspect of what? Important aspect of cost of resources. And here in this particular lecture, our intention will be to find the simultaneous behavior of time and cost for the project. Now, the project completion time can be reduced by reducing. The mechanism is called as crashing of the activities. I will explain this concept in detail. What do you mean by reducing or crashing? The normal completion of time of critical activities. And if you remember previous lecture, we have seen what do you mean by critical path. We also studied what are critical activities. So the crashing of normal completion time of critical activities will increase the total cost of the project. If the crashing of normal completion time of critical activities will increase total cost of the project, but what is again important, but the decision maker will always look for trade-off, the very important catchy word, trade-off between total cost of the project and total time required to complete it. Again, focus your attention on this total cost of project. Students, keep one thing in mind. When we say total cost of project, this total cost of project is divided under two heads. In that, first head is direct cost. First head is direct cost, whereas second head is indirect cost. First head is direct cost, second head is indirect cost. Any project may be government project or private project, will consist of number of activities to be performed in some predefined order, in some predefined precedence relationship, which will consume time as well as resources, and resources will consume cost. That cost is divided under two heads, direct cost and indirect cost. Again, we will see what are the contents in this direct and indirect cost in further slides. So let's move ahead. Now you can see here very important aspect, project crashing. Remember the term crashing. Crashing is the act of reducing time duration of particular activity. Crashing is nothing but act of reducing time duration of particular activity. For example, suppose there is activity called A, and that activity which we are calling it as A takes 5 days of normal time, 5 days of normal time, without any means. If we perform it in a given pace, it will take 5 days. Now it may be possible that by applying some means we can finish that activity A in 3 days. We can finish activity A in 3 days. This particular concept is called as crash time. Here the same activity A needs 5 days to complete, but if I deploy more manpower, more resources to the activity as per given constraint, and if it can be finished within 3 days, that is referred as crash time. Now you see there is difference between this normal time and crash time. Means what we did is, if we find here delta t, for this case delta t is 2 days. Delta t is 2 days. How come we get these 2 days? It is difference of normal time 5 days minus crash time 3 days. Meaning this activity can be crashed by 2 days. There is misunderstanding amongst a student. I will make it clear at this point only. They take or they interpret this crash time as the duration by which it can be crashed. It is wrong. Crash time is the amount of time required to perform that activity, and by how much duration that can be crashed is the difference between normal time and crash time. You have to keep that in mind. So crashing of completion time of critical activities, to reduce the project completion time would certainly require extra resources and cost. So here I have explained this sentences with the help of these particular figures. Now here we have noted that normal time is 5 days for activity A, crash time is 3 days, so we can reduce the time duration by 2 days. That will not happen of its own. For that you have to deploy extra resources, and when you deploy extra resources, all resources are associated with cost. So it is but obvious that when you go for normal time to crash time, it is bound that cost of completion of that activity will increase. It may be possible that now here 5 days, and suppose it takes 200 rupees resources for 3 days. Suppose the amount of money required is rupees 300. What I have written, 5 days if you perform, total activity consumption of this cost is 200 rupees. If I reduce duration from 5 to 3, I have to spend 100 rupees more. Students, now here what we did is, normal time was 5 days, crash time was 3 days, and 5 minus 3 was your delta t, which was 2 days. But if you see crash cost was 300 minus normal cost was 200. So here delta c, this was delta t comes to be rupees 100. Means, how to interpret this? Suppose I am crashing this activity by 2 days, how much additional expense I have to bear? 100 rupees. And this is nothing but what is mentioned over here, that you have to bear extra cost. Let us understand this particular figure. Here on y-axis it is cost, and here behavior of direct cost is shown. So here it is direct cost versus, on this particular axis it is activity time, direct cost versus activity time. Now focus your attention on this curve, focus your attention on this curve of, on y-axis it is direct cost, on x-axis it is activity time. Time means this is activity time, activity time versus direct cost. Now it's very simple. If I take this point, this is point B, if I take this point and if I project it like this, so correspondingly on time scale I get normal time, I refer this as NT. From 0 to this point is normal time, and if I project on this axis, y-axis, I get for corresponding normal time cost, which is called as, I will write here abbreviation NC, normal cost. So normal time, T time, and normal cost, and normal C cost. What I did is, from this point I have projected on x and y axis. Suppose we crash this activity, given activity, by some duration, means time will reduce, and suppose time comes from this point to this point like this. Suppose now we take this point A. Now drop perpendicular from A on x-axis, it will cut activity time axis at given point, which is referred as crash time, CT. NT stands for normal time, CT stands for crash time. Means, again, get it very clear that this is the amount of duration, normal duration, which you need to perform that activity. If possible, by some means, you can complete this particular activity during this time period from 0 to this point. Means you have crashed this activity by this duration. And what is that duration? Delta C. What is that duration? It is difference of, not delta C, it is delta T. It is delta T. Delta T is nothing but NT minus CT. So this is the time period by which we have crashed the activities. Now, coming to the costing. See here, the moment you attempt to complete that activity before normal time, as we have mentioned here, extra cost is incurred. We have seen here. So see that cost is increasing from this normal cost point, from this point to, if you drop projection here, this is crash cost. So earlier, for normal time, your cost was this. Now for crash time, your cost is this. Means cost has inflated from this value. Earlier your cost was this much. When you have performed this activity within normal duration, now since you have crashed this activity, your cost component has increased tremendously. So increase in, this is total CC, crash cost. By how much amount it has increased? The increase amount is this much, and this is obtained by taking difference of this CC from 0 to NC from 0. So CC minus NC. So we get del C is equal to, that is difference in cost is equal to crash cost minus normal cost. Got it? Now, we know now, it's very sure that we'll be again I will be explaining this in problem. We'll be only crashing critical activities. And if we crash critical activity which are possible to crash, time duration will reduce but cost will increase. Now here we have seen that by crashing this activity by the amount of 2 days, our total cost incurred was 100 rupees. So per day, if I want to find the per day cost, for that what is done in mathematics is, now this is curve. What we are getting is a curve. So to find this per day, what we are doing is we are assuming this curve as a straight line, linear approximation. And once we know that we are shifting from this curve to linear approximation of point AB, so we can find then slope of this particular line AB, and which is nothing but del C by del T. So this slope is indicating you per time unit cost of crashing. What is giving? Per time unit crash of crashing. Now here understand this by this example. For this, suppose I want to find slope, it is del C by del T. So this comes to be 100 by 2 as 50 rupees 50. This is the formula, this is the application. Now this particular slope is called as cost slope. This particular slope is called a cost slope. What is the interpretation of this slope from operations research? Trade-off, cost, time trade-off analysis is, it is the amount of additional expense. It is additional expense on particular activity if we want to reduce the time of activity by unit time. The unit time may be 1 day, 1 week, 1 month as per the structure of the problem, as per the units of activity given. What we have to remember, it is additional expense in reducing activity duration by unit time. I am using the word unit time, whatever may be the unit. So that is behavior of, this is behavior of direct cost. Direct cost. Now this is very important. You have to have linear approximation of linear relationship for this curve. Now let's go ahead. Here, as mentioned, what we wrote earlier is total cost of project, any project, total cost of project is equal to direct cost plus indirect cost. Direct cost plus indirect cost. Any project in real life, any project in real life will have two parts. One is direct cost, other is indirect cost. Now we have seen, just now we have seen the behavior of here it was time and here it was direct cost. In last slide we have seen behavior like this. Very important aspect we are studying now. So this is this part. But any project will consist of, again, one aspect of indirect cost. Again, if you consider this as time on x-axis and this as indirect cost on y-axis, we see two different behavior. One is like this and other is like this. You might have studied this in some subject. So this stands for fixed cost and this stands for variable cost. See here, direct cost is behaving like this, indirect cost is behaving like this, consisting two elements, fixed cost and variable cost. See, at this point 0, in spite no production, you have to have your fixed expenses incurred every time, and this variable cost is the amount of expenses incurred on actual production of the units in the industry. But for production of those units in the industry, you need to have some resources with you which will always consume, in spite whether you produce or you do not produce, it will consume some fixed amount. Example, simple example, rent on buildings, taxes, electricity, whether you produce or not produce, your administration staff will be there. they will be consume some electricity. So in spite of whether the quantities are produced or not produced, you will have some expenses as a fixed cost. And here this line starts from this point, means depending on the quantity produced, you will have variable cost. This direct cost consists of two components. One is direct labor plus direct material. Direct labor plus direct material. Now how to interpret this? Suppose we are thinking of automobile engine. Now automobile engine is having parts like crankcase and some internal parts, connecting rod, camshaft, crankshaft, bearings, piston, cylinder, all that. All these material comes under direct material, and the operators who process those direct materials, components of that engine, are treated as direct labor. Mind well, the person sitting in administrative building will not be the part of direct labor. Direct labor will be the person who is working, who is giving value addition, who is doing value addition on this material. The person who is doing value addition on the material is referred as direct labor, and the material used for that is direct material. So any project, may be small or big, will comprise of two costs, direct cost and indirect cost. See, as a OR consultant, OR specialist, we are never interested in only this one or two part. We are interested in total cost of the project. We are interested in total cost of the project. And now see here the figure which I am drawing. Here again, this is time on x-axis. Of course, this is activity time. This is on y-axis total cost. Total cost. Now, very important, see the behavior. We know this. This is nothing but direct cost. We know other component which will now start from 0. This is nothing but indirect cost. Two components. Now students, what is our interest here is to get this curve, which is total cost, addition of direct and indirect total cost. Now you focus your attention on this curve. Here if I think this point, so for this point, suppose I think this point, for this point the corresponding time will be this and total cost will be this. Here if I move in backward direction towards left, you can see it is gradually going down, and at this point it is minimum total cost. Other way to get this minimum total cost is, what we can do is draw a line tangent to this total cost curve parallel to x-axis. If I did like that, If I do like that, what I'll get? This is the line, and what I'll do? I will drop perpendicular from this touching point on time axis. So here we get very important time, one this and other this. So this particular point is called as optimum time, and this point is called as minimum total cost. I will explain this. Now see here, if you go by crashing of the activities, if you go by reducing of the activity, the graph reads that by reducing the time duration of different activities up to particular point, it's okay that your total cost will reduce. But if you pay your attention to the left side of this point, students, you can find for this point, for this point, for this point, for this point, though you are reducing the time, but your cost is increasing. Your cost is increasing than your total minimum cost. So what, as a OR specialist, we have to do in time trade cost analysis is, cost time trade analysis is find optimum time for performance of any project and corresponding minimum cost. Optimum time and corresponding total minimum cost. So in analysis, our aim will be always to find TO by crashing the network and get corresponding minimum cost. So we have to achieve the balance between what? TO and total minimum cost. Total minimum cost. So this is how one can explain cost time trade-off curve. This is called as cost time trade-off curve, and we have to go on reducing the time of the network up to this particular point. So same thing I have shown here on this particular chart: direct cost, indirect cost, total cost. And now you focus your attention on this activity. Again, I have explained through example that normal time and cost, crash time and cost, here it is normal time in days was 5 days, cost was 500 rupees, crash duration was 3 days, and it is 300 rupees. The unit is rupees. Here the unit is rupees. Here it is days. Here it is days. Any activity for under consideration. So the cost slope behavior is as it is given. Cost slope is difference of what? Del C by del T, which comes to be here del C is 200 by, again this is 2, so rupees 100. So how to interpret this particular table is, suppose I want to crash this given activity by 1 day, because cost slope gives you cost of crashing per day, per time unit. Since the unit is days, I am saying cost of crashing this particular activity by 1 day is rupees 100. How 100 rupees answer you got? Delta C was 500 minus 300, so 200. Delta T was 5 minus 3, 2 days. 200 by 200. I think it is clear now. Now, suppose a problem is given like this, and we wish to find the optimum duration. How to proceed? See, this network is given a problem. A project consists of, what is given in the problem is, a project consists of 6 activities as shown below. The following table gives normal duration, one data, crash duration, other data, third data, normal cost and crash cost, and indirect cost is 70 rupees per day. In this numerical, you have to be very careful for units. Don't forget the units for the day, for the activities, and what is the unit of cost. Find optimum project duration. Optimum project duration means what is asked is TO and corresponding minimum cost. Now here what you have to do is TO, what you have to find is TO equal to what? That is to be analyzed, and minimum total cost for this particular project for given TO. Now how to interpret this? See here, we have seen how to draw network from the given logic in PERT and CPM problem. So these A and B are starting activities and C, D, E, F are further depending activities. This is normal duration given in days, normal cost, again cost is in rupees, this cost is in rupees, this duration is in days. Means you can normally do activity A within 8 days. You can finish that activity A in 6 days also, means you can crash it by 2 days. There may be the scenario where you cannot crash activity. There may be a scenario where you cannot crash activity, and that scenario we can witness under activity C. See, activity C, normal duration is 2 days, crash duration is 2 days, means there are no chances of crashing activity C anymore. The activity for which, remember one thing, the activity for which del normal T, NT and crash time CT are same cannot be crash. If NT and CT are same, that activity cannot be crash. That you have to remember. Now first what you have to do is you have to draw network from the given logical relationship, and then we will be plotting that network on time scale version graph. How to do that we will see. Before that, what we have to do, we have to add this normal cost column, which will give me direct cost of the project. So here if I add all these cost of this activity A, B, C, D, E, F, 100, 250, 300, 400, 500, it comes to be, summation comes to be rupees 580. This is very first step that we have to do when we start analyzing any project for cost time trade-off analysis. What is to be done? Summation of the column of cost under normal cost. So 580 rupees is the direct cost. This indicates you direct cost. We have seen that any project, for project total cost is equal to sum of direct cost plus indirect cost. Total cost of the project is sum of direct cost plus indirect cost. So I could get For initial phase, direct cost as 580 rupees. Now, next step will be to draw the network and to represent that network on time scale analysis on graph paper. That is easiest way, that we'll see. Now, see here, from the logical relationship, from this relationship, A and B are independent activity, C depends on B, D depends on A, and looking to given the relationship, if you recall, we have studied this aspect in earlier lecture of PERT and CPM, how to draw critical path. I also mentioned that you have to give the symbolic representation, you have to write the formulas. That we have already studied, and therefore I am giving you the snap of solved network for the given relationship. Now here we can see here these values as 18, this is 18 and this is also 18, means the completion time for this project is 18 days. Normally, if we want to complete this project as per normal duration, this project will consume 18 days. This project will consume how much days? 18 days. 18 days. 18 days. This we have seen that how to draw critical path and all that. Here this activity A and this activity D represent critical activities. A and D represent critical activities. Now, some hints I am giving you. You have to focus on the aspect of indirect cost. Indirect cost. Indirect cost. Here it is given rupees 70 per day. In this problem it is given indirect cost as rupees 70 per day. Now, one thing you have to keep in mind, when you reduce the time duration of any project, initially if you consider normal time, the indirect cost will be for the duration of normal duration. For this case it will be for 18 days. So means if I want to add indirect cost into total cost, it will be mathematically 18 days into per day, that is 18 into 70 will be the indirect cost. But the moment you reduce the time duration, your project completion time also reduces. So number of days also reduces. So indirect cost also reduces. See, when you crash, direct cost increases and indirect cost decreases. This is very important. When you crash any network, any activity of the network, direct cost will increase, but simultaneously indirect cost will decrease. But how to get balance between these two so as to get TO and minimum total cost? How to get the balance? Only crash, one key I am giving you now. Only crash critical activities if possible. This is very important, if possible, because there is no point in crashing non-critical activity. Non-critical activity crashing will only increase the cost, but it will not reduce the time of your network, because critical path will remain same if you are crashing non-critical activity. We have seen that critical path is the path of longest duration, and if you are unnecessarily crashing non-critical activity, you are not reducing total project duration, you are not reducing the time of critical path or maximum time of the project. On the contrary, you are adding burden to the project by performing non-critical activity at faster pace, at earliest, which is useless. So, very important point, only crash critical activity. First point. Second, in critical activity, only crash those activities having cost slope, less than equal to indirect cost. Only crash those critical activities for which cost slope is maximum equal to or less than equal to indirect cost. Because why this point is important? Suppose cost for particular activity is 30 rupees, and indirect cost is 70. So 30 rupee cost slope means additional expense in that activity by reducing it through one time unit is 30 rupees. On the contrary, if I reduce that activity by one time unit, I will save 70 rupees. So what I am saving 70 rupees per day as an indirect cost. At the same time, I am expending 30 rupees. So what is net saving to me? 70 rupees minus 30 is net saving, net gain to me, with reducing in the time duration by one time unit. Suppose indirect cost is 70, cost slope is 50. What is the net saving? 70 minus 50, 20. Suppose indirect cost is 70 and it is 60, difference is 10. Suppose both are 70, indirect cost is 70, cost slope is 70. As such, there is no saving in the cost, but time duration is reducing. But if you are increasing the cost, then you have to expend from your pocket. So third key is crash those activity for which cost slope is less. Three important points you have to remember: crash only critical activities. Second, crash activities having cost slope max equal to or less than indirect cost per day. If there is tie that there are more than one activity having cost slope less than indirect cost per day, crash that activity first, which is having least cost slope. Now see here, this is the graph paper. Now what you have to do on this graph paper? You have to plot, you have to start from this 0, mark this as 0, I am just giving you hint how to proceed. 0, then 1, 2, 3, 4, you have to select scale. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Here I have taken 18 because we are having 18 days. First thing what you have to do is you have to draw critical path along straight line. So you have to start from top to bottom. So 1, I think it is 8 and 10, So 8, A 8 and D 10, 18. It is 5, D 10. This is the first step, and then you have to progressively draw the diagram. Complete this chart. This is the arrangement I have shown. Same I am explaining now through the chart. See here now. This is the chart drawn. Here you can see the same network which we have drawn earlier. Here this is critical path 1, this is 2, A of 8, and this is D of 10. And then simultaneously you have to also draw the in between points like B activity, C activity, then floats till end, and this activity F3. So this is the first step, and here E of 5, EF is on this 5, like that. Crashing is done step by step, and you have to first find the slope. How to find that slope? See here, these are the activities given. Delta C, delta T, indirect cost was given rupees 70. Indirect cost was given rupees 70. So cost slope was calculated by the logic del C by del T. Different cost slope was obtained. Then total cost, in very first slide we have added this 580 as a normal cost column, 70 into 80. So you get your amount 1840 as total cost of the project for 18 days. If you complete that project in 18 days. Now step by step reducing this, crashing this activity and plotting this on the chart will yield optimum duration. See here, we have to focus on activity A and D being critical activity. Since A and D are critical activity, focus on the cost slope of A, focus on the cost slope of D. Students, A can be crashed by 2 days, A can be crashed by 2 days, D can be crashed by 5 days. Cost slope is 50 and 60. Compare this cost slope of 50 and 60 with rupees 70. If you compare this cost slope of 50 and 60 with rupees 70, 50 is less, so we will crash A first, then followed by D. So here simultaneously you have to make table that activity to be crash. Here I have crash activity A, for which cost slope is 50, duration crash was 2, cost of crashing was 100, 18 minus 2 gives me 16, and for 2 days saving in indirect cost is 40 because 70 per day, 70 into 2 140. Net saving which I got is rupees 40. It is difference of this 140 saving, 100 expense is 40. I have to subtract this 40 from 1840 is my initial cost. So 1840 minus 40 is 1800. So 1800 is the cost when I crash activity A. Similarly, we have to analyze the project. Next is the turn for activity D. If you crash that, your cost comes to be 1780. Next, it is combined crashing of F&D. Your cost comes to be same 1780, but remember, find this duration of 12 days. Here it is 14 days. So for 14 days your cost is 1780. For 12 days also your cost is 1780. Importantly, further, if you again intentionally try to reduce the duration like this from 12 to 11, see your cost has increased. So compare 1780 with 1795. This has increased. So this is minimum total cost. This is minimum total cost, and for this minimum total cost, your TO is how much? 12 days. So in this way this problem is completed. So for this particular case, optimum duration is 12 days and corresponding cost is 1790. So here we have completed the aspect of project cost trade analysis, and we have finished with unit number 4. From next lecture we will start with unit number 5, that is replacement models. Till time, practice the sums and practice the problems pertaining to PERT, CPM and project cost analysis.